Hello viewers, welcome to my channel KK Concepts of Electrical Engineering. Inductance of two conductors transmission line. Let us consider two conductors. Let this be A having the radius A and B having the radius A itself. The distance between these two conductors is, let this be D, and the current in both the conductors are I in opposite direction. This conductor possesses both internal and external inductances. So inductance L equals to L internal plus L external. So let us try to find out the internal inductance of the conductor. That is Li. So I am considering conductor having the radius A, in which I am considering an angular ring having the radius R, and the width of this ring is, let this be dr. So when you consider the radius R greater than 0 less than A, the flux density B is given by mu I R divided by 2 pi A square. This relation we got from the previous videos. Please refer the link given below. The flux d phi is given by integral R to A B dot dr. Now for this, mu I by 2 pi A square are the constants. So R to A R dr. Now let us find out this. Mu I divided by 2 pi A square R square by 2 of A to R. Now this is mu I by 4 pi A square. R is A square minus R square. Let the J current in the conductor divided by area by A square. This is inside conductor. Now let the J equals to I dash divided by 2 pi R dr, current density in angular ring. From these two, I dash is given by I of 2R dr divided by A square. Now actual flux linkage is given by this new 2R dr by A square of d phi. D lambda is given by 2R dr divided by A square into d phi is mu I by 4 pi A square minus R square. Total actual flux linkage inside the conductor is given by lambda, that equals to integral 0 to A d lambda, that equals to integral 0 to A 2 times, so mu I divided by 2 pi A square divided by e to the power of 4 minus R square divided by e to the power of 4 R dr. Lambda is equals to, I am taking out mu I by 2 pi, then integral 0 to A, the first term, that is A square e to the power of 4, so A square will remain 1 by A square R dr minus R square into R dr divided by A to the power of 4. Now mu I by 2 pi, 1 by A square will remain 1 by A square. Now R, if you do that, then R square by 2, which is 0 to A minus R to the power of 3, R square into R to the power of 3, so R to the power of 4 divided by 4, 0 to A divided 1 by A to the power of 4. When you simplify this, you are going to get mu I divided by 2 pi 1 by A square by 2 minus, here also substitute that, A square by, sorry, A to the power of 4 by 4, 1 by A to the power of 4. The zero values, if you substitute, then you're going to get 0. So I'm not considering all those things, which is nothing but half minus 1 by 4th. 1 by 4th you are going to get. So mu I divided by 2 pi 1 by 4, that is mu I by 8 pi. This is the actual flux linkage inside the conductor. So inductance L inside the conductor I is given by mu I divided by 8 pi current I. Then you are going to get mu by 8 pi. This is in Henry. So we got the internal inductance of conductor 1. But in our case, that is 2 wire transmission line or 2 conductor transmission line, we'll be having 2 conductors. So Li in this case is 2 conductors multiplied by internal inductance of a single conductor, that is mu by 8 pi. Then you are going to get mu by 4 pi Henry. In our case, I is given by mu by 4 pi. We found only internal inductance of a conductor. Let us find out the external inductance. That is La. Let us consider a point P in between these two, which is at a distance of x from conductor A. Then this distance will be d minus x from B. From the previous videos, the flux density, which is at a distance of x, is given by B mu r by 2 pi x. So this is already proved. The link is given in the description below. Please go through it. The flux density due to B. So this is due to conductor A, let this be, then this is due to conductor B. That is given by mu I divided by 2 pi, and the distance between conductor B and P is d minus x. The total flux density due to conductor A and B on point P is given by B equals to BA plus BB. That equals to mu I divided by 2 pi is the common term, so 1 by x minus 1 by d minus x. Let this. We need to find out the total flux linkage. Given by pi equals to integral b dot, in this case along x is varying or the distance is varying, so along dx. We need to find out the flux in between A to d minus A. We found the internal inductance, so we need to find out the external inductance. Mu I divided by 2 pi, that is 1 by x minus 1 by d minus x of dx. So I'm taking common mu I by 2 pi common. Now if I do 1 by x, then I'm going to get log x. So limits are a to d minus a. Similarly, minus log d minus x, the limits are a to d minus x. Solve this. Mu I by 2 pi, that is log x is nothing but log d minus a minus log a, sorry, this is d minus a, second term minus log d minus a, minus of minus plus, minus log d minus a is nothing but mu I by 2 pi. This is log d minus a by a minus dt gets cancelled, log plus d minus a minus log a. Mu I divided by pi 2 times of log d minus a by a. 2 times gets cancelled. Flux phi is given by mu I divided by pi log d minus a by a. This is our flux. We got the flux. All these things to the base E. Now external inductance is given by flux per current, that equals to mu I by pi into I log d minus a by a to the base e. Obviously, it will be there. Phi gets cancelled, then you are going to get Le is equals to mu by phi of log d minus a by a. Usually, L is given by n phi by I. But for conductor system, n equals to 1. So this is why I have taken phi by I here. Now, the inductance of two-way transmission line L is given by Li plus Le. That implies the first one, Li, is mu by 4 pi plus mu by pi log d minus a by a henries to the base e per meter. Until now, we found Le and Li in per unit values. To simplify and write inductance of a two-wire system, that is L equals to mu by pi 1 by 4 plus log d minus a by a to the base e Henry per meter. Now, if you consider a special case that if d is greater than a, then this formula is going to change as L equals to mu by pi 1 by 4 plus log d by a, that is Henry per meter. If you have any suggestions and queries, please mention in the comments. If you like this video, please like, share and subscribe. Thank you for watching the video. Please stay tuned for more videos.